Hi there. My name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in the previous lectures of guitar amplification and effects, we've spent a lot of time looking at the Mesa Boogie dual rectifier, and we've also looked at Fender amplifiers, but if I recall correctly, we have not looked at any Marshall amplifiers. This is a grievous oversight on my part, which I shall rectify today. We've previously looked at single-ended power amplifiers. Now we will look at push-pull power amplifiers. In particular, we'll look at the Marshall 18-watt combo. Now, this schematic was created by pedalmonkey.com. If you actually go to pedalmonkey.com, all that shows up is the logo. So I'm not sure what happened to Pedalmonkey, but I wanted to give them proper credit. The power supply is up here in the upper right corner, which is kind of funny because it makes it look like the speaker is blasting at the power supply. That, of course, is not the case. So we will spend this lecture and the next lecture focusing on the power amplifier that drives the speaker. The power amplifier in the Marshall 18-watt combo is driven by this long-tailed pair phase splitter. The long-tailed pair phase splitter is responsible for creating non-inverted and inverted versions of the signal coming in here, although there's also a potential signal coming in from this other preamp path here, in which case, let's see, if you're coming in this direction, then this would be the inverted version, and this would be the non-inverted version. Oh, and I should mention that unlike the cathode phase splitter architecture, the long-tailed pair can provide gain, so it also doubles as another preamp stage. So the long-tailed pair can take inputs from this normal set of inputs or this tremolo set of inputs, or it looks like both at the same time. If we focus on the normal preamp, you might be tempted to think this is some sort of long-tailed pair, but it's not. It's really just one common cathode amplifier that happens to have two possible input tubes. The notation here on the schematic indicates that this is a normal jack. If you don't plug anything in, there's a default connection that's made, but if you plug something in, this default connection is broken, and this terminal here is hooked to whatever you're plugging into it. Same thing down here. If you plug into the low input, then you have your signal going into the tube in the top here, but as far as the high input goes, that's normal to ground. So that's kind of like this. All right, if you plug into the high input, then your signal is going to go this direction, and then it also will connect here, and that gets normaled through the low jack also. So you wind up taking the signal and putting it into both grids. Okay, so plugging into the low jack means that you're just going into this grid. Plugging into the high jack means that you're going into both grids. Wow, that's complicated. Oh, and if you plug different sources into both inputs, it looks like this is disconnected and this is also disconnected. And then there's no real difference between the two inputs. So it looks like it will mix the inputs without making this one louder than this one or vice versa. Okay, so that's how the normaled ending with the letter D jacks work in the normal ending with the letter L channel. Let's see, the output of that common cathode amplifier goes through this tone and volume network and then goes into the left side of the long-tailed pair. But there's another channel that goes into the right side of the long-tailed pair. So the other channel is the tremolo channel, and the output of that goes through this tone and volume network up this direction to the right side of the long-tailed pair. Here we have a speed control and an intensity control. I never really took the time to suss out how tube-based tremolo circuits work. For the purposes of this class, you can consider them to be wonderful and magical. They're fun circuits, but the details aren't very important for our current discussion. So our main object of study is going to be this power amplifier. Now the power amplifier is hooked to the long-tailed pair through these 0.01 microfarad coupling capacitors. For the purpose of our current discussion, I'll assume that these are shorts as far as our signal goes. In a previous lecture, we saw the effect that these capacitors can have on the low frequency response. We won't worry about that here. I'm going to model this as if the outputs of the long-tailed pair are jammed right into the grids of the tubes. So the general idea is that one of the tubes is presented with a non-inverted version of the signal, say coming in from the left, and the other tube is presented with an inverted version of the signal. Both of those have their plates sent to the transformer, but they're going in the opposite direction, so the signals wind up combined constructively in the transformer. Now, technically speaking, there's 3 different ways to bias this. One of them is to bias in a Class A mode where both tubes are active the whole time. Another way is to bias it in a Class B mode where one of the tubes is active or the other tube is active, and when one tube is active, the other one is off. The most common way is to actually bias it in a Class AB mode where during some of the cycle, both tubes are active to varying degrees, but during other parts of the cycle, only one of the tubes may be active. Class AB tends to provide a nice compromise between efficiency and low crossover distortion. Remember that with the Fender Champ that we looked at, the power supply for the plate and the power supply for the screen were the same. Here they're different. Here the plate is supplied by a 325 volt supply, whereas the screen is supplied by a 300 volt supply. And the actual voltage at the screen will be a little bit less because there's this 100 ohm resistor between the power supply and the screens. This push-pull amplifier is cathode biased with a 125 ohm resistor, and like every output stage I've seen, it's fully bypassed. As an aside, notice that there's this marking 50 to 500 microfarad. Other information on the schematic here says that different instances of this amplifier were examined, and there were a variety of capacitors found in this roll. In a previous lecture, we looked at the effect that this bypass capacitor has on the low frequency response. We're not going to worry about it here. As far as the biasing goes, this is an open circuit. As far as the actual signal goes, we're going to assume that this is a short. The use of cathode biasing here contrasts with the power amp stage in the Fender Bassman that we will look at in a future lecture, which uses fixed biasing. In this lecture, we're going to look at the biasing, and then I'll perform a large signal analysis to compute the actual power delivered to the speaker in the next lecture. So, to deal with the biasing, I'm going to take this and split it into 2 separate common cathode stages. To do that, we'll take this 125 ohm resistor and write it as 2 250 ohm resistors in parallel. And similarly, we're going to take this 100 ohm resistor and write it as 2 200 ohm resistors in parallel. And if you wanted, you could play the same kind of tricks with the capacitors here, but it's not going to be terribly important for what we're going to do. So doing that kind of trick, we can redraw half of this push-pull stage like this. So 2 200 ohm resistors in parallel would give me 100 ohm. 2 250 ohm resistors in parallel would give me 125 ohm. And for completeness, if you put some 25 to 250 microfarad capacitors in parallel, you would get 50 to 500 microfarad like seen on the schematic. So splitting this into its DC bias and quote-unquote AC small signal circuits, remember that the transformer is essentially a short at DC, so we'll analyze this. Now, there are a variety of data sheets that include what are called triode-connected curves that are the kinds of curves that you would get if the screen and the plate are hooked together. These are very convenient for figuring out biasing issues if the plate and the screen are given the same voltage supply, because usually the voltage drop across this resistor, if you have it, isn't very big. So you can consider VSK and VPK to be the same. Now here it's a bit more complicated because these are different. But I've generally found that trying to figure out the biasing, if you have this kind of situation where these supplies are different and you are really making an effort to take that into account, is extraordinarily painful and takes a lot of trial and error. So what I'm going to do is I'm just going to pretend for the moment that this is 325 volts. It's not true, but let's pretend and see what happens. We'll come back to this point. Anyway, if I do that, I could use this set of curves and draw a load line and a grid line, just like we did with the preamp stages where we had voltage gain with a 12 AX7 or something like that. So to draw a load line, at one extreme, we could imagine that there's no voltage dropping across the resistor. That is the no current case. And then all of this 325 volt is dropping across the pentode. And I should mention this is from the Mullard version of the datasheet for the EL84. Anyway, we can draw one point along the horizontal axis at 325 volts. So get ready for it. Here it comes. Whee! There it is. Oh, and I should also mention, I think there's a bug on the way this datasheet is drawn. This 250 volt should be one grid point to the right. If you count this number of grid points, you wind up with these 9 grid squares. If you count these, you wind up with 11. So I'm pretty sure this is in the wrong spot. Just keep that in mind. Now, if I try to use our usual trick of assuming that all of the 325 volt is dropping across the resistor, I'm going to get a current that's so big it's not going to even remotely fit on this graph. So I have to pick a different point. What about the VPK equals 300 volt? That's kind of nice because it's the right end of the graph here. Okay, so 325 volt minus 300, that will give me 25 volt divided by my 250 ohm resistance. So that's going to give me 100 milliamp. So that's here, and I can draw a point for that. Ready? Here it comes. Whee! There it is. All right, now I can draw a line connecting those dots, and that's my load line. Now I need to intersect that with a grid line. So I'm going to try a grid to cathode voltage of minus 10 volt and minus 12.5 volt. Plugging in minus 10 volt gives me a current of 40 milliamp. Oh, one very important point that I should make is that when it says that this is the anode current, as in the plate current, and you see an A here, that's a bit of a misnomer. This is sort of for a super plate that includes the screen. So I think this is very confusing. It's much better to think about this as being the cathode current. So imagine scratching out the word there and calling it cathode. I don't know why they do that, just to confuse us. Anyway, that gives us a cathode current of 40 milliamps. So I can draw that here. And let's see, for minus 12.5 volt, dividing that by 250 ohm, and of course putting the minus sign here, then we wind up with a 50 milliamp cathode voltage. But now I run into a bit of a dilemma. If I take this 50 millivolt mark and draw a line over, well, it's going to intersect this minus 12.5 volt line somewhere that's off the graph. So what I tried doing is just taking a straight line and kind of fitting it to this end. Now, this is not a straight line. Of course, it is going to curve, but I don't know. Anyway, hopefully we'll get something close enough. So taking this extrapolated minus 12.5 volt line and drawing in this 50 milliamp line, we can draw a line between those points to give us this purple line, and that's our grid line. Now we can find the intersection between the purple line and the red line, our grid line and our load line, and that gives us something of 45 milliamps as far as my cathode current goes. To compute the grid to cathode bias voltage, I would take the cathode current and multiply it by my 250 ohm cathode resistance. I rounded that to minus 11 volts, and that's more or less in line with what I see on the graph here. And then as far as the plate to cathode voltage goes, I would take my 325 volt power supply and subtract the voltage at the cathode, which would be 11 volts, giving me 314 volts. And that pretty much matches up with what I would read off of the graph here. Now, I would like to know how much of this cathode current belonged to the screen and how much belonged to the plate. So I found this graph on the data sheet that shows the screen current for a variety of plate to cathode voltages with a bunch of lines corresponding to different grid to cathode voltages. Now, one caveat is that this is for a screen to cathode voltage of 300 volts. Now, the power supply for the screen is 300 volts, but we would need to subtract the cathode voltage to get the actual screen to cathode supply, so that would be something like 289. And this also doesn't include the current that's being dropped across that 200 ohm resistance. We'll come back to that point. Anyway, I'm going to hope that this is close enough to this that we can get a useful result. So, a grid to cathode line of minus 11 volt is pretty close to this minus 10. Kind of looking at the pattern here, we might have a line somewhere around here. So, if I were to draw a line like that, and then put in the plate to cathode voltage, that would be 315. Well, it's actually fairly constant for a wide range of plate to cathode voltages. Let's see, I wind up with something like 1 milliamp for my screen current. I don't know why. I don't really have a good explanation of why this doesn't feel right, but this feels small to me. I feel like this should be more like 3 milliamps, just generally based on experience. But again, I don't really have a good reason for saying that. It just feels odd. Anyway, let's roll with it. The plate current is then 45 minus 1, aka 44 milliamp. Anyway, if I believe this number, we can refine our estimate of the screen to cathode voltage by saying that the actual screen to cathode voltage is going to be 300 volts minus that drop across this 200 ohm resistor, and then minus the 11 volts that's sitting here at the cathode. But if I plug in the numbers for this, well, 1 milliamp times 200 ohms, that's just 0.2 volts. So that's almost nothing. And I'm just going to say that, well, this is approximately 289 volts and use that in all of my remaining computations. And even if this was a bigger number, this is still going to be a relatively small number relative to this. So I'm not going to worry about it a whole lot. So let's check to make sure we're not blowing up the tube. I can compute the dissipation for the plate by taking the plate to cathode voltage, multiplying it by the plate current, and that gives me 13.8 watts. As far as the screen dissipation goes, I would multiply the screen to cathode voltage times our assumed screen current, and that gives me 289 milliwatts. So let's check these numbers relative to the data sheet. Now, the data sheet tells me that the maximum plate dissipation is 12 watts. So that's a little strange because 12 watts is less than our actual computed number. So that initially made me think, okay, well, if I messed up in estimating the screen current, then my estimate of the plate current is too high. But let's suppose that the screen current was something like 5 milliamp. So that would mean that my plate current would be 40 milliamp. And that would still give me something that's bigger than 12 watts. That's giving me 12.56. So no matter which way I slice it, this is really pushing the limit of the plate dissipation. And this doesn't seem to be terribly uncommon. I've seen this in other amplifiers that I've analyzed. Of course, I could be analyzing them all wrong, but this does seem to be a consistent thing. People will push the plate dissipation, at least in guitar amplifiers, in power stages in a way that they won't in preamp stages. It feels to me like pushing this plate limit so much would limit the life of the tube. A theory I have is that maybe this 12-watt figure is designed for something like a television or a radio where people might leave the television in their house on all day long. Whereas, say, if you're on the road playing shows every night, maybe you'll use your tube amp a couple of hours a day for the gig, with, of course, some additional time for sound checking and rehearsal and practice. But that's different than leaving a television on all day and all night long the way some families do. My other theory is that maybe guitar players are just willing to put up with their tubes taking more abuse because they really want designers to push the limits of the amplifiers, because unlike a standard television or radio sitting in a house, the guitar player has to compete with a drummer and possibly a horn section. Of course, there's also the possibility that I just messed up this analysis. Maybe I made too many approximations. Who knows? Let me know your thoughts in the comments below. Okay, now let's check the limit on the screen dissipation. So that's going to be a limit of 2 watts. And as is typical of all of the designs I've seen, we're well within the limit. People don't push the limit on the screen dissipation. In fact, I could replace this one with a 5 and still be within this limit. Before we close out, I'm curious as to how much power this cathode resistor needs to dissipate. So, I took my 45 milliamp, that's my cathode bias current, squared it, multiplied it by this resistance, and came up with 506 milliwatts. You could also take 11 volts, square it, and then divide it by the resistance, equivalent formulas. But remember, this is only half of the amplifier. The actual resistor in the real amplifier needs to be able to handle twice that. So it needs to be at least 1 watt, and here they've spec'd it as 5 watts. In the next lecture, I'll use these bias values we computed in this lecture to do a large signal analysis and see if we can actually get 18 watts out of our alleged 18-watt amp.